So I'm assuming you've read the problem probably several times and you're probably really irritated with it by now. So I'm not going to go into what it's saying, but I'm going to draw a quick picture just so we have one to look at. Maybe you're wondering how we're going to do this. And the equation I used that worked, and that's probably the best and maybe only equation that works for it, is Kepler's third, which you've talked about in class already, but Kepler's third is the time of the period squared equals the constant times the radius cubed. And this is really handy in this problem specifically for one reason, and that's that it has something in common whether you're using it for y or for x, and that is k right here. And we know that k is equal to 4 pi squared over the gravitational constant times the mass. But the great thing about this mass is that it isn't just any mass, it is the mass of this guy right here. Yay! So it's the mass of the object that's being revolved around. So this is the same for both x and for y. So we can use a variation of Kepler's third law, one for x and one for y, and then solve for the constant k and plug it into the other equation in order to find the time of the period for y, which we'll be able to use to find how many revolutions y has gone through in the 5 years that x has over the course of this problem. So we're going to kind of... And then it looks like we don't have all of these variables that we're solving for, but it turns out we actually can find the time of the period of x based on the information we're given. So in the problem, it says that in 5 years, x has gone 90 degrees. And this is really helpful for us because we know that the time of the period is how long it takes to go 360 degrees, or 1 revolution. So we can easily find that if it were to be 4 times as long, it would be 1 revolution. So we can say that the time of the period of x is 20 years. Hey, that's handy dandy. So we can plug this in and easily solve for k. There we go. So we can go ahead and we can plug this in right up here. Don't be too hard. You can say that the time of the period of y squared equals 400 over rx cubed times ry cubed. Now it looks like we have 3 variables in one equation, which usually doesn't work, but the nice thing is it actually will work here because of the ratio we're given in the problem. And the ratio we're given in the problem is that the radii of the 2 planets is 3 to 1. So we know that it takes 3 of radius y to equal 1 radius x. And that's really convenient and helpful for us. And for me personally, I'm going to kind of move this around to where we have ry equals 1/3 r of x. So then I'm going to plug that in up here. So we'll have time of the period of y squared equals 400 times rx cubed, and then it'll be 1/3 rx cubed, or 1/3 rx, sorry, and the cubed up here. So then with some, multiplication, we've got this right here, which is super handy dandy because we can cancel these guys out. So we know that the time of the period of y squared equals 400 over 27. And we can square root these. And I'm kind of going to move the math to the next page. But we know that the time of the period of y equals the square root of 400 over 27, which if you plug that into your calculator, you will see equals 3.849 years. And we know it's in years because we originally plugged in 20 years for the time of the period, and that was the only time we ever plugged in. So the units are maintained throughout the problem, and that's how many years. But that's not what the problem's asking. It's not asking for the time of the period of y, it's asking for how many revolutions it's gone through so far. So to find that, we just have to set up a simple ratio, which isn't too hard. We know that with one revolution, it'll be 3.849 years. So we can say, okay, how many, we can just call it x, how many revolutions will it be in 5 years, which is how many years have passed in the problem. And so some cross multiplication, we get 5 equals 3.849x, which then gives us 5 divided by 3.849 equals x, which you're going to find equals 1.299, which is about 1.3 revolutions. Yay! And if you're doing this off of Mr. Askey's homework, that should be the answer he gave you, which is nice that he gives you that because you can always check to see if your answer's right. But yeah, that is the problem. So good job, guys. Talk to you later.